We created this a couple of years ago, and the reason we created this was that initially we went out to speak to about the dozen banks we reached out to in Europe about our credit intermediation idea. The first thing they said to us was, "Look, this is a very volatile asset class. At the time, it was probably 70 times more volatile than equities now, probably 30 times." They said, "Look, let's fast forward 5 years, and let's say we have credit lines with all these counterparties to trade these assets. The biggest issue we have from a risk perspective is if there's a big move, we don't want our clients to get wiped out. So how do we ratchet down credit lines to reduce how much trading activity is happening? How do you put speed bumps on to slow down the speed of this before it happens?" And they were very open and honest and just said, "Look, our value at risk models, our normal distribution curves, they just don't work with this asset class." So they said, "Look, it's on you. Can you build something, and can you give us something to help us with the risk?" So we kind of went away and said, "Okay, that's a pretty difficult and tough ask, but yes, we can do." And we built a very interesting piece of tech. And what's very unique about this is that it uses true AI, so it uses deep learning AI. And again, look, I think the reason we don't talk about it too much is unfortunately every single person in the world now has AI. I get so many emails from people telling me about how amazing their AI is. When you ask them about what the mechanics are of how it's trained or what algorithm they use, they have no idea because it's automation. It's not really AI. If you cast your mind back to probably 2012, there was a really interesting inflection point. And the very bright chaps at NVIDIA decided to say, "Hey, could we repurpose graphics processors for parallel processing?" And that's exactly what they did. So if you think about a piece of code or a string of instructions, a normal CPU will take that very long string and it will process it in a linear fashion, and it might take it, I don't know, let's say 100 seconds. If you have a parallel processor, i.e. the GPU, it will take that strip and it will slice it up into 1,000 different pieces. It will process them all at the same time. So we'll do it 1,000 times faster. And that was really the first key component. The second key component was in 2012, there wasn't really that much data. And that kind of changed in 2017, 2018, where you saw a huge increase in the amount of data that was available. So you could actually have a proper data set and a training set to train the AI agents. And when I discovered deep learning, what was remarkable about it, and this is something that really does blow my mind, is that the way in which we use that data source is that we take the raw data, we give it to the AI agents, and we don't tell it what good or bad is. So it's unsupervised learning, which is very unusual, and it's unstructured data. So these two things are very, very big, and they're very key components to why our AI outcomes are so profound. What happens is that these AI agents actually they learn what they're being trained for, i.e., they work out what you're trying to solve, which I still find completely crazy. That they actually work out what I'm asking them to do without being told. So that's how I define AI. The best way to understand how well this works is to watch it in action for a couple of hours. And 85% plus of the time, it accurately predicts moves before they happen. We even have a couple of hedge funds that are using it to trade and generate P&L. Not that you should do this, not a trading system. It's really for, I guess, managing risk. So if you're using technical analysis to trade, you can use the indicator to size your trades, or you can basically fade into reversals. But I wouldn't use this as a metric alone. Could this be developed into an algorithm to trade the markets? Yeah, absolutely, definitely. It's got a whole bunch of uses that we haven't explored yet, but we definitely will do. So why is this different to a whole bunch of stuff that comes out of Silicon Valley? And the biggest difference on this is the evolutionary theory. So look, I'm sure you're all familiar with Darwin and his theory of evolution. So the fundamental problem with Darwin and Darwinian evolution is the hypothesis was everything is in the genes, right? So essentially, what that basically means is that it is about survival of the fittest. The problem is we had this thing called the Human Genome Project back in the 90s, and the results of the Human Genome Project kind of said otherwise. So what basically happened was the hypothesis was that one gene equals one protein. And it was thought, okay, well, the human body makes about 124,000 proteins, therefore we must have 124,000 genes. The answer is no, we don't. We have 25,000 genes. So then the question was, well, how the hell do we make the extra 100,000? And the answer is, well, they are expressed as a function of our environment. So if you go back in time, there was a Frenchman called Jean-Baptiste Lamarck who had a slightly different evolutionary theory to Darwin, and that was termed Lamarckian evolution. And rather than survival of the fittest, it was more about survival of the most compatible, of those that were the most collaborative. The big difference between us and a lot of platforms that use AI is we don't use one AI agent. We use dozens and dozens. And the way in which we work is we look at which groups of these AI agents work best together to make the best predictions. So that's the first difference. The second difference that we have that's very radical is really the way in which we use quite unusual bits of technology. So there's a post-processing system that's used that's very, very unusual. We use a fractal geometry. Again, something that's developed by Google for creating images is used to discern market information. The reason we do this is because if you look at the geometry of markets or the geometry of the human face, it's fractal geometry. You look at the geometry of markets as fractal geometry. So it's a very powerful tool. So it's a combination of these things that make it very unusual. The way in which we chose the target vectors and the algorithm also has an impact. So if you look at Google, for instance, they use an algorithm called random forest for their AI. And one of the biggest criticisms I've seen leveled at AI is the concept of overfit. So when you're training what these AI agents, sometimes what happens is the training data set has an adverse impact on really those AI agents. So when they come across real world data, the outcomes they predict are wildly out of kilter from where they should be because of the issue that they've been tainted or tarnished by the data set that's been used. So we use a derivative of this called isolation forest. And I guess the simplest way of explaining this is if you imagine within any data set, you normally have some kind of clustering around a mean. What isolation forest does is it looks at the outliers and it measures the distance of those outliers. And it works on a very simple premise to say, look, this outlier seems so far away from this mean cluster, it was probably created by something other than whatever the creative force was for the main distribution of that data, i.e. something was done to that piece of information or that data set to create an outcome that is radically different to the rest of it, i.e. there is something about to happen that is anomalous. So one of the very unique things about isolation forest is in inverted commas, it's not actually a predictive model, even though it makes predictions. So what this does is it takes away and takes completely out of the equation this concept of overfit, which again is I think quite radical. And what effectively allows us to do is allows us to have a real purity of that outcome. And then of course there was a very long period of refining the data set. If you take Bitcoin, for instance, that's the target vector, and there's a whole bunch of context vectors. And we went through a very, very long iterative process of selecting and then removing a whole bunch of things. So we started off, I think, with about 250 context vectors. We reduced it down to 126. If, for instance, Solana, as it did today, went from 0 to 75%, what does that 75% mean? Well, it means that there's a 75% probability that there's going to be an asymmetric move or a volatility event in the next 60 minutes. But what's that made of? And via the API calls, you can actually look at it and say, well, actually, 35% of that was made by on-chain data, 10% might have been related to FX, 5% might have been fixed income, another 5% might have been equity related. So you can get a real good feeling for, what is the provenance? What's the origin of this? Where is this number coming from? So it's not a black box model. It's very transparent. We built it like that on purpose so that you can see exactly how it works. And we are looking to expand this, so we are beta testing foreign exchange as well, and I think the combination of those two things could be very powerful. Eventually, we'll also be looking to maybe bring out some algorithms to maybe then potentially allow people to trade that asset